Okay, so we're going to look at homework 7-3. This will be the first part, so hopefully get through at least the first half of the questions or so. Okay, but anyway, question 1. Two equal magnitude forces are applied to a door at the doorknob. The first force is applied perpendicular to the door, the second force is applied at a 30-degree angle to the plane of the door. Which force exerts a greater torque about the door hinge? Okay, so in this case, both of those two forces, here's my hinges of the door. So the doorknob would actually be over here somewhere, right? Okay, so the door itself has that length, which would be the length of the lever arm. If we want to know what the relationship between their torques is, which one has the greater torque, we know that the force is equal in magnitude, but one of them is applied perpendicular and one of them is applied at an angle. Okay, now they give us the 30-degree angle, but really regardless of that, by applying the force at an angle, only part of that force is now going to be perpendicular, and therefore, whereas this entire force is acting perpendicular to the lever arm, only a portion of this second force is. Okay, so the first force that's applied entirely perpendicular is going to get the highest magnitude of torque, right? And if you just look at the formula, right, torque equals force times radius times sine of theta. So if we have any angle at all involved, that's going to decrease the value of our force. Okay, so again, the one that's applied perpendicular, that's going to produce the greatest torque about the door. Question 2 is a lot like a question you've seen before, actually, if you go back to homework 2. Okay, so if the sum of the external torques on an object is 0, then the sum of external forces on the object also must be 0. Okay, so again, the question here really is, does the external torque being 0 imply that the force is also 0? Well, if we think about torque, so I'm going to choose my door here, and then again, so this is the hinges of the door, that's my axis of rotation. Okay, so I know that the torque of the object is 0. But if I choose a situation where maybe I'm applying a 10 Newton force halfway and then a 5 Newton force at the end of the door, we know that because torque is dependent on both the force and the radius, right? So even though this force is lesser than the 10 Newtons, if I were to double the radius, the torque of this would be the same as the torque caused by the 10 Newtons. So even though the forces are different, the torques would be the same. Okay, so using that reasoning, we can see that again, the torque produced by this first 10 Newton one could very well be equal to the torque caused by the second one. So maybe my first torque is equal to the second one. If the forces are different, the only thing that tells us is, so if my force, if for instance the force of the second one there is lesser, the only thing it tells me is that radius better be more to compensate for that. Okay, so just because the net torque is 0 doesn't mean the net force has to be 0, because if I look at these two, right, even though the net torque would be 0, my net force on this door would still be my negative 10 newtons pushing down and my positive 5 newtons pushing up. So my net force would actually still be 5 newtons or negative 5 newtons depending on which way we define it, yeah, which obviously is definitely not 0. So then that tells us that this is not necessarily true. So this does not have to be true. It could be true. Definitely is possible, right? If I hit the hinges, if both of those forces happen to be applied at the same point, then they would produce not only the same torque, but they would also have to have the same force to produce that same torque. So it is possible, but it doesn't have to be true. Question 3 is a good concept question. This is one that you see a lot. It's one I can definitely see a number of formats where they try to trick us with this, right? So if the sum of both the external torque and the external force on the object is 0, then the object must be at rest. Now hopefully most of us just remember from the definition, maybe even easier to start with forces as we look at this, but if we know that the net force equals 0, that does not necessarily mean the object is not moving, right? The only thing this tells us for sure is we know the net force relates to mass times acceleration. So the net force equals mass times acceleration. Since the mass of an object can't be 0, if the net force is 0, that tells me that the acceleration has to be 0. But that doesn't mean the object's not moving, right? It only means the object is not accelerating, it's moving at a constant velocity. Okay, so the same type of rationale works with torque. Okay, so as we've started to see, torque causes angular acceleration. Well, if the net torque is 0, then again, all that tells me for sure is the angular acceleration is 0. That doesn't mean it's not rotating, that doesn't mean it's not moving, it just means it's not rotating faster and faster and faster, and it's also not slowing down. Okay, so just because the net torque is 0, just because the net force is 0 does not mean the object has to be at rest. It could simply be moving with a constant velocity or a constant angular velocity. Okay. So could be at rest, but it doesn't have to be. And then the last multiple choice question for this homework assignment, a lot like a question again we've seen going back to homework 2. So you've got the croquet mallet, it's suspended here. So the fact that it's suspended here tells me that the center of mass is at that location. Again, if you've got an object that's being suspended, the only force acting on that object would be its force due to gravity. Well, the reason that this mass isn't tipping over is because the force due to gravity is acting exactly at that axis of rotation. Right? If I was to suspend it from over here, the force due to gravity would be acting over here and would cause it to torque counterclockwise as we rotate around this axis of rotation. But since it's hanging at that point and since it's not tipping, that tells me that has to be the center of mass. Okay, so I know my center of mass right here. So really the question becomes, does the mass on each side of the center of mass have to be equal? And that's really the same type of question we've seen before. And the answer to that is no. Okay, and the reason for that is if we go back to our formula, right, to calculate the center of mass depends not only on the mass but also on the position of the mass. Right, so it accounts not only for the mass itself but the position. So if we think of this hammer head as a single mass, if we think of the handle of the hammer as a separate mass, okay? So if we think of those really as just two masses, okay? They don't have to have the same mass, because if we look at the head of the croquet mallet, the head of the croquet mallet is going to be much closer on average than maybe the center of mass for the pole. Right, so those two distances between the center of mass, x1 and x2, are going to be different, which tells me that the masses can also differ. It tells me the masses do not have to be the same. Okay, so this is maybe a counterintuitive one, but the masses do not have to be equal. Okay, the fact that the head of the mallet here is closer to the center mass tells me that this is actually in fact the more massive one because its radius is smaller. Okay, so the piece with the head of the mallet does in fact have a greater mass. So question 5 is another center of mass question. Obviously not a multiple choice this time, but another hopefully pretty straightforward calculation. Now, you do notice that this is an xy plane, so we do have two dimensions here we have to pay attention to. But as we saw in class, to deal with this, all we're really going to do is we're going to find our center of mass in the x direction. Okay, so we've got 3 different points here. We've got 3 different masses. So I would find each of those positions, right, times each one of those masses. And then I would divide that by the entire mass of the system, so mass 1 plus mass 2 plus mass 3. Okay, so I would do this for my x measurements, my x coordinates, and then I will ultimately end up doing the same thing for my y coordinates. So I'll take y1 times m1 plus y2 times m2 plus y3 times m3, and then once again over the total mass of the system. Okay, so in and of itself, as long as we know the approach to take on this problem, not a terribly difficult problem. Okay, they tell us that the first mass is 6 kilograms and is at 0, 0. So the x coordinates are 0, the y coordinates are 0. So if I'm plugging in now, I know my first mass is 6, its position is 0, so to keep it consistent over here, its position is 0, its x1 is 0, the mass is 6, plus the second one is at a position of 3 meters for my x value. Right, so my x2 is 3, that second mass is 4 kilograms, plus the third mass is once again at 0, and then it has a mass of 2 kilograms. Okay, so plugging that in, and then I take that over the mass of the entire system, so 6 plus 4 plus 2. Okay, so as I do this, as I calculate my center of mass, again, hopefully you agree it's not too bad here. It ends up being 12 over 12, and I end up with 1. So what that tells me is the position for my center of mass in the x direction is 1 meter away from the origin. Okay, so my average x position, my center of mass for the x position, is at 1 meter. Then I do the same type of thing for y, right? So just completely separately, I look at my y values, so I look at my y values, and then I use the mass as well. Okay, so the y value for that first one is also 0, so 0 times 6. So really that first mass of 6 we ended up not needing for either of these problems. Plus the second y position, which is also 0, times its mass of 4. Again, that negates that one. Plus the third y position. Okay, so its third y position is 3, and then it's times a mass of 2. And then once again over the total mass of my system, which is 12. So this one ends up being 6 over 12, which is 1/2 or 0.5. Okay, so the center of mass for my entire system then would be my x position, comma, my y position. So I'm really just finding the coordinates for my center of mass. Okay, and I now know that is 1 meter from the origin in the positive direction and 0.5 meters from the origin in the positive direction. Okay, so even though there's two dimensions, as long as we keep them separated, right, keep our vertical and our horizontal measurement separated, not too bad to solve this particular. Okay, so question 6 probably be the last question we get in this first part here, but we'll go ahead and work through this again. We've seen this now a couple times in class, and hopefully you agree it's not too bad, but can be kind of tricky, right? Can be tricky until we get comfortable with it. So a uniform beam of weight 254 sticks out from a vertical wall. Lightweight cable, we don't have to worry about the mass of the cable, which is nice. Okay, it connects to the end of the beam, and it connects from the end of the beam to the wall, making an angle of 65 degrees. What is the tension in the cable? What is the force exerted on the beam by the wall? Okay, so obviously a diagram helps us out here. So I've got my relatively vertical wall here, right, and then I've got the beam that's sticking out from the wall. Again, not quite horizontal, but it's me, so it's close enough. Okay. Anyway, I don't know what happened there. I'll clean that up. So we've got the tension that's connecting the wall then to the beam. Okay, so my tension connects at the beam down here, and it connects up here at the wall. We know the angle it makes is 65 degrees. So we do have that angle to work with, 65 degrees. And we want to find the tension itself, and then we want to find the force exerted on the beam by the wall. So the way that I always suggest approaching these type of problems, whether you're doing it with numbers, whether you're doing it just by looking at the relationships, identify all of the forces at play. Okay, so I will say, as I look at this picture, make sure we go ahead and cut off the rest of that. The tension is supposed to be at the end of the beam. Okay, so there's no beam beyond that point. So go ahead and imagine that's not there anymore. Okay, but anyway, okay, so identify all the forces at play. So the fact that it's a uniform beam of 254, again, we've seen before, uniform is important because it tells me that that force is applied straight from the center of that beam. Okay, so they actually don't give me the length of the beam, so I don't know how long this beam is. Maybe I'll just call it a length of L. But I know then that the force of gravity of that beam, that force of gravity, that 254 newtons, would be acting at a distance of half of L. It'd be acting at a distance of L over 2, since it's a uniform beam. Okay, and that actually will be a big important piece for us. Okay, so we've got that force acting. The only other force we know for sure we have acting, at least right now, is tension. Right? Tension pulls off at that angle. Well, because tension pulls off at that angle, we know that it pulls partially over and partially up. The fact that it pulls partially over tells me I have to have something going at the wall too, right? I have to have at least an x component over here at the wall because the beam's not moving into the wall, and so I know those two x components have to be equal and opposite. Okay. The question mark becomes, do I have a vertical component at the wall? Do I have something holding it up? And usually that's going to be yes. But let's go through this problem and look at exactly why that's a yes and where we can go. Okay, so when we look at this problem, we start working through. Again, we look at just the forces. The problem is the wall is too much of an ambiguous case, so I get stuck. Okay, so if I just try to use the net force, I get stuck, right? I don't know. I know the force of gravity is pulling down. I know this component of tension is pulling up, but those two aren't necessarily equal because maybe I have this force acting too. Okay, so unfortunately I have to do torque, right? I'm not able to just do my force due to gravities. I'm able then to do torque. Okay. So typically for torque, I'm going to choose that to be the axis of rotation. Okay, so I'll go ahead and choose that to be the axis of rotation. The reason I want to do that is to eliminate the force at the wall. Okay, and so regardless of whether there's one component there or two, by choosing this to be my axis of rotation, in terms of torque, these aren't going to produce any torque now because they're acting at that axis of rotation. They're acting through the center. Okay, so I don't have to worry then about the torque. Okay, so instead what I'll do is I only have two forces now that contribute to the torque. So if I kind of just resketch this picture, here's my axis of rotation. I know the force of gravity is pulling down, and then I know my tension is pulling up off at that angle. Okay, so I've got my tension pulling at the angle, I've got my force of gravity pulling down. I know that the beam is not rotating, and what that tells me then is that the torque caused by the force of gravity has to be equal to the torque caused by the tension. So then my force due to gravity times its radius needs equal to, now with the tension, because the tension is at this angle of 65 degrees, I just want the vertical component, so I just want the sine component. So I'll go ahead and say t times sine theta, and then times the radius to that tension. Okay, so the radius to the gravity and the radius to the tension. Fortunately, I'll have to stop here. I'll pick this up in the next one too.